So I was asked to give help to solve this identity. Not solve, but verify the identity because the left side does in fact equal the right side. So when I get ready to do this, I know I can only work with one side, either the left or either the right. And most of the times, I start to take a look at different things like I know cotangent and cosecant. I can change those to cosine and sine because they're the ones I feel most comfortable working with. Also, when I have a single term on one side and two terms on the other, I'm thinking about I want to combine those. So I think I'm going to work with the right side. Now, what do I need? Well, can I use an identity? Is there one of the identities like the Pythagorean identities I can work with? Also, can I make a side a single term? Which, yeah, the one I looked at, it was two terms, excuse me, and I'd like to make it into one term to equal the right side. And again, a lot of times work with the biggest side. The other thing I mentioned is, can I change to sine and cosine and work with those because I feel more comfortable. Now, one of the identities that we have, and of course you have this big identity sheet, okay, but I didn't put the Pythagorean ones on here for you, but the ones that are the most popular are going to be this guy right here, which I used to make students memorize. And you start to pick up a pattern. When it's the cosine, I know they're both cosine and the sine is opposite. When they're the signs are the same, but it's the sine of the first, cosine of the second, cosine of the first, sine of the second. And after you use them quite a bit, you become familiar with them. The other one that is pretty fun, not fun, but in class, when I would teach the class, it was fun to come up with because basically the sine of 2 theta would be the same as going the sine of theta plus theta, which is 2 theta. So I get sine theta, cosine theta, sine theta, cosine theta, and that gave me the two cosine thetas. So these basically get derived from what's up there, and putting a little thought into it is what you come down to. So again, the one that's not on that list, the Pythagorean identities, starts with the sine squared plus the cosine squared equals 1. And that would be an x or, and again, in the world that trig works with, normally the angle measures are represented by Greek letters and values, number values are x. So this isn't a good one, but you'll see it and it's okay. And the reason I bring this up is if I said the sine squared of 12 degrees plus the cosine squared of 12 degrees, that's going to always equal 1. Now, the other two Pythagorean identities that you use a lot would come from, what if I take this and divide everything by sine squared? So for this row, I'm going to divide by sine squared of theta. Sine squared divided by sine squared gives me 1 plus cosine squared over sine squared gives me cotangent squared, and 1 over the sine squared is the cosecant squared. So this guy comes right from the first Pythagorean identity. If I go back to that first one again, and now I divide everything by cosine squared, I have sine squared over cosine squared, which gives me tangent squared. Cosine divided by cosine is 1, and 1 divided by cosine is secant. So the most popular one you see is the sine squared plus cosine squared. This one down here, the tangent squared, that comes up quite a bit. But when I'm taking a test, I would write these down right away so that I have them in my short-term memory and I can regurgitate them onto my identity sheet and be able to use them. Okay, so back to the problem. I said something along the lines of, I'm going to pick a side because we can only work with one side. I'm going to go with this right side, and I'm going to turn this into sines and cosine. And my reciprocal identities, I have all those simple identities. What can I bring into play? But I do know converting these into sine and cosine is going to give me something like that. Then I get excited because I did say something about combining terms. So I'm going to combine this into making it cosine of x minus 1 over sine of x. Okay? Common denominator, sine of x. I'm going to square everything. When I square a binomial, again, it's cosine x minus 1, cosine x minus 1. I have to double distribute. A lot of you call it FOIL, but I get the cosine squared of x minus the cosine of x minus the cosine of x gives me minus 2 cosine of x plus 1 over the sine squared of x. Okay. So now I start taking a look at this, and I what do I have up here? What can I work with? Doesn't seem like I got anywhere with this. But now when I look back up here and I go, wait, this is cosine x minus 1, cosine x minus 1, I'm going to go back and leave it as that. Cosine x minus 1, cosine x minus 1. Now, I didn't get anywhere with any of that. Even though cosine squared plus 1 looks familiar, it's not. So I'm going to now change sine squared. And if I go back to my Pythagorean identities, sine squared is the same as 1 minus the cosine squared. I'm going to come back over here and make this 1 minus the cosine squared. Why? Because I can factor that. In my numerator, I have cosine x minus 1, cosine x minus 1, and now I have 1 plus cosine x, 1 minus cosine x. Okay? So I'm still really close. And when I take a look at this, I go, oh, no, wait a minute. This is the same as negative 1. Because if I rewrote this as negative cosine of x plus 1, I factor out a negative 1, I get cosine of x minus 1. I can go and cancel these, and I have a negative 1. So now I come to my next line. I have negative 1 times cosine of x minus 1 over 1 plus cosine of x. And if I distribute, I get negative cosine of x plus 1, 1 plus cosine of x. Take it up, and that's where I went. So I had to play around with it. I used a Pythagorean identity. I used some factoring. I used some canceling. Practice is what makes you good at verifying identities. But as you can see, they do sometimes take some work. So I hope this helps.